Start today's seminar. Welcome everyone. Thank you for joining us for another installment of the Graduate Environmental Engineering Seminar Series. Just a couple of reminders that we are keeping everybody on mute and preventing sharing a video during the seminar. But if you have questions for our speakers at the end of the seminar, please just raise your hand or type a note in the chat and we will unmute you and you can again ask your questions, or if you post them in the chat, I may read them or have the speakers read them for you. Also, another reminder that if you want to receive the continuing education credits, documentation of that continuing education, please send an email to Dr. Eric Seagren, who is one of our speakers today. So I'm going to go ahead and introduce Dr. Eric Seagren and Alex Waypa. So Dr. Seagren is someone most of you know. He's a professor of environmental engineering in the Department of Civil and Environmental Engineering at Michigan Tech, and he has been on the faculty here at Michigan Tech since 2010. Prior to that, he was on the faculty at the University of Maryland in College Park, also in the Department of Civil and Environmental Engineering. Prior to starting his appointment at the University of Maryland, Dr. Seagren completed a postdoctoral fellowship at Northwestern University. He received a BS in civil engineering with distinction at the University of Nebraska in Lincoln, and an MS in sanitary engineering from Iowa State University. He received the PhD degree in environmental engineering at the University of Illinois at Urbana-Champaign. Dr. Seagren's research broadly is in the field of environmental biotechnology, especially in the its application to groundwater bioremediation, and that led to his interest in the topic that he'll be presenting today with Alex Waypa. And his research has been recognized with numerous awards, including Outstanding Doctoral Dissertation Award from the Association of Environmental Engineering and Science Professors, a National Science Foundation Early Career Development Award or Career Grant, and the Rudolph Herring Medal from the American Society of Civil Engineering. Currently, Dr. Seagren serves on the Transportation Research Board Standing Committee on Geoenvironmental Processes, and he serves on the Civil Engineering and Industry Advisory Board for the University of Nebraska-Lincoln. Alex Waypa received her BS degree in environmental engineering from Michigan Tech, and she's currently a Master of Science degree student in environmental engineering at Michigan Tech. And Alex has been doing research with Dr. Seagren and also helps out with our wastewater surveillance project here at Michigan Tech. So without further ado, I will turn things over to Dr. Eric Seagren and Alex Waypa.
Okay, thank you. I have to apologize. Alex is my co-author on this presentation, but I'm going to just give the presentation today. And Alex, I'm sorry about that, but we just did not have time to get coordinated to share presenting duties. So you're going to just be stuck with me today. But Alex has been my great assistant throughout this work and helped a lot with running the experiments and data analysis and preparing slides, and it's been a great asset in doing all this work. So thank you, Alex. So our presentation today is on borehole dilution theory. We're going to demonstrate there was application of that to unpumped wells for the purpose of semi-passive in situ groundwater remediation. And so without further ado, here's one of the images from our experiments, and we'll talk more about those later. I presented some of this work about a year and a half ago, and it'll go beyond what I presented previously. Okay, so when we're this work is really motivated by some of the challenges we face when we're cleaning up contaminated groundwater in situ or in place. Generally, this requires that somehow we get the contaminant or contaminants in contact with either a reactive material that's going to enhance the transformation or sequestration of the contaminant, or the co-reactants that are required for the reactions that we're interested, whether abiotic or biotic, to proceed. So for example, I primarily are interested in the area of in situ bioremediation. If we have biodegradation of petroleum hydrocarbons, we've got plenty of electron donor hydrocarbon here, and there's usually plenty of hydrocarbon degrading microbes in the environment, but usually what we're running out of is oxygen. And you can see there's a pretty high oxygen demand, 9.5 moles per mole of, in this case, shown as hexane as a representative petroleum hydrocarbon. In addition to that, we may need other amendments in the case of bioremediation, things like acids and bases to control pH, nutrients, etc. So, you know, these amendments all might be available in the natural environment, and if we don't have too high of contamination levels, it may be just fine. But typically, that's not the case. And I show a scenario here of a petroleum spill, a refined petroleum product spill at a gas station. We've got a high concentration of hydrocarbons leaching into the subsurface here. The preferential electron acceptors like oxygen, nitrate getting used up very quickly. So we have an anaerobic core to our plume where there isn't any oxygen. We just have oxygen available on the margins of that plume as a result of advection and dispersion and diffusion from the unsaturated zone. So that is more typical that, you know, we need to get these extra amendments here. Sorry, I don't know what. So this is really the challenge, right? How are we going to get these missing reactants like oxygen in? We have to somehow get them into the subsurface and bring them into contact, in the case of bioremediation, with the microbes that are mediating the reactions of interest. And this is really one of the most challenging aspects of in situ remediation, is how do we get those materials into the subsurface and mixed with the contaminant and the microbes in the right locations. And there's a variety of techniques that have been developed over the last few decades, you know, ranging from very active approaches where, say, we're doing water circulation to circulate amendments through the contaminated zone, creating a in situ bioreactor, or using air as a carrier in the subsurface, either in the saturated zone or saturated zone via air sparging, all the way to very passive techniques where we're putting in material and letting it slowly release into the subsurface. And so these are a variety of techniques been delivered. We're going to, in this work, we're focused on the semi-passive in situ remediation approaches, and I'm going to talk about a couple of those here. So one what we might call a semi-passive technique is the use of permeable reactive barriers, or PRBs, that we place in the path of contaminant plume. And I show you here, we've got contaminant source and some drums that are leaking, contaminating the subsurface and the saturated zone, the contaminants being carried by the groundwater plume, and then in their path, we place a permeable reactive barrier that has been excavated using excavating equipment, and then filled with either reactive material. So this could be like activated carbon to sequester, absorb the contaminant, or zero valent iron to release electron donors to stimulate reactions, or it could be amendments that introduce amendments that are reactants that are required to promote the reactions within the barrier and downgrading the barrier. So, for example, if we have a nitrate plume that we need to remediate, we might, and we want to promote heterotrophic denitrification, we might add something like compost or some other organic material that's going to slowly release organic matter that could stimulate the heterotrophic organisms. Or we might want to add a material that's releasing oxygen, and that'll be one of our focus topics in this presentation. That's going to release oxygen into the barrier and then let it move down gradient with the groundwater flow. So this is a very good approach, but it does have limitations because we can only excavate a trench that we can then backfill so deep. And so if we want to go deeper than 50 feet or so, we're going to probably need to do some kind of approach, as is shown here, where instead of using a trench, we use a discontinuous permeable wall that's constructed from a series of closely spaced unpumped wells. So these are wells that aren't being pumped, but they're a borehole with a well screen into the subsurface in the path of the contaminant plume. These wells can, similar to the PRB, function as an in situ reactor. So we could put activated carbon or some other reactive material in there. So then in that case, we're interested in the flow into the well and treatment inside the well, or they could be like the PRB, releasing amendments into the subsurface to stimulate abiotic or biotic reactions down gradient from the well. So here the key is, well, how closely spaced do these wells need to be so I can get coverage across the plume? And that's really what we're interested in here. I don't know. I have this so-called magic mouse, and the only thing magical about it is it does things that I don't expect it to do, one of which seems to be flipping among slides. Anyway, so oxygen, like we talked about early on, is one of the key requirements for aerobic biodegradation. And so a number of companies have developed materials that we could put into a PRB or an unpumped well to release oxygen on subsurface and stimulate aerobic degradation of petroleum hydrocarbons or other compounds of interest that are degraded aerobically. I give you an example here. PeroxyChem is a company that produces a proprietary compound called Permeox. I only mention them because we use their product. They were willing to share it with us. And so we'll be talking more about that later on. But these proprietary materials are usually some kind of a mixture with magnesium peroxide or calcium peroxide or urea hydrogen peroxide that will release oxygen and into the subsurface. And usually they've been formulated in such a way that they will release it in a kind of controlled, slow way. So here I show the reaction for calcium peroxide reacting with water and releasing half a mole of oxygen for every mole of calcium peroxide. You notice also it's resulting in production of calcium hydroxide. So we get a pH change, and we'll talk more about that later here in case of an increase in pH due to the addition of the hydroxide anions. Now, the Permeox that we use comes in two forms, as shown here. It can be a kind of a powder, so you can make a slurry that you could directly inject into the source area using direct injection techniques, for example, or you could mix it with backfill into the contaminated zone, or using the more granular form, we could apply it in a PRB or unpumped remediation wells. One way that that's done, and I show here some images at the bottom of the slide from a company, Regenesis, which also makes a product called oxygen release compound, ORC, very similar to the Permeox material. And one of the ways that they implement this is via these filter socks. So these are socks, as we show on here on the slide, where they are put in these permeable socks. It can be lowered into a well. They're tied together. This was a remediation at a railroad siding. And you can see here they've tied several of these socks together that can be lowered down into the well. And this, illustrates one of the advantages of the unpumped wells is that we can go to much greater depths than we can with the PRB. Here we can go to 100, 200 feet, or what's required to reach the plume of concern. And I should say also that although I've illustrated here vertical wells, and that's what we're focused on in our laboratory simulations, this could also be done with directional drilling and horizontal wells that allow you to reach areas underneath structures or very narrow plumes, etc. So it could be done with horizontal wells also. So Permeox is one of the chemicals we'll be looking at. So the overall goal of this project was to gain some insight into how to modeling this release of slow release amendments into the subsurface, especially through arrays of unpumped remediation wells, or perhaps we could be doing this via monitoring wells that have been repurposed. In our case, we're focused on wells, unpumped wells that are installed vertically, perpendicular to the flow of the contaminant plume. Now, although this has been a fairly popular practice to use these kind of compounds, our feeling is that the models that have been used, and I'll describe those to represent what might happen in the subsurface, have not really been experimentally evaluated to our knowledge. So that's what we set out to do. And the tool we're using is what others have used to describe this, but I think we looked at it a little more closely, is borehole dilution theory. So this is what happens when the flow of groundwater reaches an unpumped well. The well has a higher hydraulic conductivity or permeability than the material around it. So this affects the flow. The water wants to flow into that well and out of it. And this theory, you know, has been around for a long time. A lot of the work that I'm referencing here goes back to a German paper from 1968 by Drost et al. And the setup will be the same. You know, we've got the zone 1, that's the well screen. So it has a permeability called K1. Outside of that, we may or may not have a filter pack, or shown here in the caption as a gravel pack. That's zone 2, which has a permeability. And then outside of that, we have the natural aquifer material. And some of the experiments we'll describe, we'll just have using what we call a natural filter pack, where the well has been installed directly into the aquifer material and there is no filter pack. So zone 2 and 3 are the same material, just the background aquifer material. So the key parameter here in borehole, relative to what we're interested in here from the borehole dilution theory, is what is usually called alpha. And that's the ratio of how wide the plume emanating from the well is compared to the internal diameter of the well screen. And as I mentioned, what causes this phenomenon is that, you know, you've got a higher hydraulic conductivity or permeability here in the well. And so the water flow lines will bend naturally into that, flow through that well, and then back out of it. So the question is, you know, what's the width of that plume that's being captured by the well and then emanating from the well in addition? And the goal here is to use, as mentioned earlier, this unpumped well as our either in situ reactor, where we put some reactive materials in there, or as a way to introduce amendments into the groundwater that then can flow down gradient and stimulate the reactions of interest downstream from the well. So this alpha parameter is really key, because we need to understand, you know, how much is that plume going to spread out when it's emanating from the well, and that's going to dictate how closely spaced the wells need to be, because we need to have the wells sufficiently close that we can cover the cross section of the plume. And initial spreading due to this borehole dilution that's going on, and that would be here close to the wells in this illustration at the bottom of the slide. And then there's some additional spreading as we move down gradient due to transverse horizontal dispersion. Now that's typically a very weak process. So you can see that the plumes are not growing dramatically, but as they move down gradient, there will be some expansion of the width of those plumes beyond what we get just from the borehole dilution effect. But again, it's a pretty weak process compared, as you can see, to the longitudinal dispersion that's going on. And this is why, you know, plumes, you know, tend to look more like a surfboard, you know, kind of long and not too thick and not too wide. Oops, where I've got, okay. So if we assume laminar flow and we have a homogeneous aquifer material without a filter pack, so I refer to that as a natural filter pack, where we have no filter pack in this zone 2. It's just the well screen is surrounded by the natural aquifer material, such as you might have a direct emplacement of the well screen into the subsurface. In that case, the equation that represents alpha based on the borehole dilution theory is given here. And you can see it's a function of the radius of the well screen, R1, and then in this case, the ratio of the permeability of the aquifer material compared to the permeability of the well screen. And if we plot this relationship as a function of the ratio of the permeability of the aquifer to the permeability of well screen, so K2 over K1, shown here on the x-axis, we can predict the alpha, or the spreading of that plume. Remember, that's the spread of the plume relative to the ID of the well screen, right? So if we have You can see here that under these conditions, if we have a permeability of the aquifer material that's at least equal to the permeability of the well screen, we can get an alpha of 2, which tells us that the plume would be spreading out to twice as wide as the ID of the well screen. So if I had a well screen that was 2 inches internal diameter, then we could potentially get a plume that was 4 inches in width. And so based on this, people at University of Waterloo, Wilson et al. 1997, assumed that, okay, let's just assume then that roughly that the plume emanating from the well screen is going to be about twice the well diameter. So alpha approximately 2 is illustrated here, and that's going to tell us the size of the plume that we would capture if we have a reactive media in our well, or the size of the plume emanating down from the well and into our treatment zone down gradient. So, based on the theory, we can see if we go back to the previous slide, we need to at least have the permeability of the aquifer and the well screen need to be similar, and we can get the maximum if we have the permeability of the well screen is at least 10 times the permeability of the aquifer. We can get a little bit greater than 2 spreading. So that was the basis of their design, and so that then dictates how close the wells have to be if we have a spreading of 2 times the diameter of the well. Obviously, this is going to take a tremendous number of wells if we have a wide, plume that we're trying to treat. So our goal in researching this topic was to investigate 2 hypotheses that we developed. One was that this borehole dilution theory modeling approach will work as long as the release of the amendments is fast relative to the flow rate of the water through the well. So if we have reactants that are very fast to react in water, like acids and bases, for example, that are almost instantaneously reacting, then we might expect the release of that reaction into the water be very rapid, and that the borehole dilution theory will describe the resulting plume down gradient of the well. The idea being that if the reaction is very fast, then the width of the plume is going to be dictated not by the reaction rate, but by the physics of the dilution through the well. On the other hand, we hypothesized that this approach would not successfully model the release of amendments when the rate of release is slow. So in this case, the rate of release, is chemically or limited and slow compared to the rate of groundwater flow through the well. Then it might not be a very good predictor. An example would be the oxygen release compounds that I mentioned. Some research in the literature by Barcelona and coworkers, and some experience I had on sabbatical in Germany suggests that the release of oxygen from these slow release compounds is mass transfer limited. And so we hypothesized that the borehole dilution modeling might not accurately predict the plume in that case, where the reaction might be limiting the process, not the physics of flow through the well. So to evaluate this, we did a series of experiments. At first, we used a natural filter pack. So just the well installed into the model aquifer. We performed these experiments in a box reactor, simulating a horizontal slice through an aquifer. So you can see here, it's a not very tall box, about 5 centimeters deep, 20 centimeters wide, 40 centimeters long enough to avoid and wide enough to avoid short-circuiting effects, hopefully with our porous media that we selected, but long enough so we could develop that plume emanating from the well screen. And then the well screen was installed into a slot here in the bottom via hot glue, and we could then interchange different well screens to look at the effect of the well screen on, and in turn the permeability of the well screen on the plume that developed. Rob Fritz built this reactor for us, and it worked just great. And you see also at the end of each end of the reactor, there is a screen that holds the porous medium in place and distributes the flow in and out of the box. And then to simulate, say we're reusing, PVC monitoring wells as our unpumped wells to release amendment into the groundwater, we used a series of PVC monitoring wells with different slot sizes. And this way, of course, there's many different well screen designs we could have used, for in terms of slots, but in this way we had a consistent, same type of well, but just only changing the slot size. So we looked at 0.01 inch slots and 0.02 inch slots. Those would be kind of your typical, more typical monitoring well sizes, and then 0.04 and 0.06 inch slot sizes, all 2-inch internal diameter. Okay. And we used 2 different porous media for these natural filter pack experiments. Most of them were done with 2mm glass beads, shown here in the upper figure, with the media installed. And then Ottawa 2030 mesh sand was our other one. And you'll see here in a lot of experiments, we've placed a transparency over where the plume is going to form, where the inside 2 lines, solid lines, represent the internal diameter of the plume. So that would be the 2-inch mark, the dash center line. And then the next 2 outer lines would represent the alpha equals 2, so a 4-inch plume. And our initial experiments were done with a non-reactive tracer. We used blue food coloring as our dye. And what we did was we periodically added it to the well screen, and stirred that water continuously inside the well at such a rate that it wasn't pushing it out of the well, but just keeping it well mixed inside of the well. And then we monitored the width of the plume emanating from the screen. We just did this using a visual assessment. So to run these experiments, first we'd add our porous medium. Sometimes we did it with a wet or dry pack. It didn't seem to make a big difference. We could determine the bulk density then based on the mass that we added and the volume. For the glass beads, it was about 1.5 grams per mil, and for the Ottawa sand, it was about 1.6 grams per mil, and the porosity range from about estimated porosity about 0.4 to 0.5 based on the particle density and the bulk density. And all these experiments, we set the flow rate so that we had an average pore water velocity of about 10 meters per day, so that we could complete the experiments in a reasonable amount of time. And the blue dye experiments are done with aqueous media of distilled water. So I show some of the results, and these I had presented about 1.5 years ago. So I'll go over this relatively quickly, but you can see the results here for 0.06 inch slotted screen and the 2mm glass beads. We got a plume width of about 3.5 inches, which would correspond to an alpha of 1.75. We did that 3 times, got very similar results. And assuming borehole dilution theory describes this, that would correspond to a K2 over K1 ratio of about 2. Similarly, with 0.4, you can see that the permeability is reduced and we get a narrower plume. We get an alpha about roughly 1.4, corresponding to a K2 over K1 of 4.5. And then going to a smaller slotted screen, 0.02, we go down to an alpha of about 1.25, 1.25, corresponding to, according to theory, of a K2 over K1 of 5.5. And then at the 0.01 slotted screen, we only had an alpha of 0.5. So the plume in that case was only 1 inch in diameter. And then we did it, to confirm this, we did it with the 0.01 slotted screen and the 2030 Ottawa sand. And you see here the effect of these relative permeabilities. In this case, we got an alpha of 1. So the plume width was about 2 inches compared to with the 2mm glass beads, it was only 0.5 alpha. So assuming well theory, this borehole dilution theory was correct for our system, and estimated permeabilities for the Ottawa sand and glass beads and the K2 over K1 ratios that we estimated, we were able to estimate permeabilities of the slotted well screens of the different sizes you can see here. And you see the dramatic effect of this slot size, 0.055, centimeter per second permeability for the 0.010 slotted screen, up to 0.63 centimeters per second for the 0.06 inch slotted screen. So we felt like, this seemed to make sense and be consistent with the borehole dilution theory. And so we used these data to make predictions about what was going to happen in the other systems we looked at. So the next step was to add reactive media. So we added reactive amendments now, either simulating pH adjustment, and we use sodium hydroxide to have a dramatic effect, or oxygen addition using the Permeox material. And then we monitored the plumes for pH effect, and that was true for both plumes, oxygen and sodium hydroxide, and oxygen for the Permeox plume, using equipment that was loaned from Presens, a German company. It's called the VisiSense camera system. And you can see it here. Basically, we put adhesive optical electrodes on the bottom of the box. So down here on the bottom of the box, they're adhered, and then we put the porous medium on top of that. And this camera then shines a light onto those optrodes and then reads the emission wavelength. And we can then, using the appropriate optrodes for pH and oxygen, we can calibrate those optical electrodes or optrodes and get the concentration in different zones. So this is kind of a cool way to follow the plume of these reactive materials. Now, in the case of sodium hydroxide, in all of these experiments with the reactive media, since we got the biggest plume with a 0.06 inch slotted screen, we focused on that. Again, 2-inch internal diameter. We used a 2 millimeter glass beads. To use the optrodes, the solution had to be buffered so that they would work properly. So we had a pH 7 buffer for the aqueous phase. And again, average pore velocity about 10 meters per day. So at the start of these experiments, we would place a pellet of sodium hydroxide, about 0.08 grams, we determined worked well over quite a bit of trial and error. Put that on the bottom of the reactor, and then monitored the pH plume emanating from the well screen using the pH optrodes adhered to the bottom, taking images every 2 or 3 minutes. So here you see this in action. Now these optrodes are sensitive to light, so we had to run these experiments in the dark. So here Alex and I were, in the dark running one of these experiments. Well, not just I'm in the dark most of the time, but we were really in the dark for this. And you can see the optrodes being illuminated by the camera, which is here at the bottom. I take that back. Really the light sources are here in the corner. I don't know, they might be kind of hard to see, but in the corners here, there's the light sources for pH and oxygen, and then the camera in the center is collecting that emitted light. So the lights are striking the optrode with a certain wavelength, and then we're capturing the image here in the camera. So in this case, sodium hydroxide, we have half of the box had optrode for pH, so the right-hand side is shown here. So you can see the background color is kind of that, well, to me, it looks kind of an orange-red, so that's around pH 7-ish, 7 to 7.5. And you can start to see this yellow zone coming out here. So we're getting there above pH 8. You start to see some fingers of high pH emanating from the well screen, similar to what we saw from the blue plume. And then if we continue to the conclusion of the experiment after 40 plus minutes, we can see that this elevated pH plume emanating from the well screen has reached its full dimensions, and very similar to in the size that we saw with the blue dye. Now, this is only showing half the plume, because on the other half, we had optrodes for oxygen. Okay. And to get that width, to estimate the width of the plume, what we did was take a profile across that. And so here you can see that as we move it, and this profile here is about midway through the plume. We have a pH here about 8.5, and then a dramatic drop off to the background 7 to 7.5 pH. And so we could estimate the plume width. Alex and I did this independently. We got a little bit different, slightly different numbers. So we need to refine our method here, but we got a plume width of about 3.65 inches, alpha about 1.8, which is very similar to what we got with the blue dye, where we had, again, an alpha of about 1.8. So here we've made a mirror image so you can, kind of imagine what the complete plume would have looked like. And we repeated this experiment with almost identical results. And here you see the second experiment performed under these conditions, a very similar plume, about 3.66 inches in total width and an alpha of about 1.8. So, these alpha values with the strong base were very consistent with what we saw with the blue tracer, and consistent with our hypothesis that for these very fast reacting materials, the plume width would be well described by the borehole dilution theory. So then we went to the Permeox material. Same conditions, I'll go through this kind of quickly, 0.06 inch slotted screen, 2 millimeter glass beads, phosphate buffer solution, 10 meters per day, roughly pore water velocity. But here we had to de-aerate by autoclaving the phosphate buffer so that we could see the effect of the oxygen amendment. And to add that oxygen material in a way that we could easily clean it out and sort of to simulate one of those filter socks, we placed the material inside a wire mesh tube with a 1-inch diameter that was inserted into the center of the well screen, and then monitored the oxygen and pH plume down gradient using the oxygen and pH optrodes on the bottom of the aquifer. So here we see early on, the plume emitting similar to what we saw with the blue dye. We see the elevated oxygen levels here on the order, over 100% saturation, maybe closer to 120% saturation, and the background down here at something less than that. We'll see that better in the profiles. And the plume continued to develop, and we see that after time similar in size to blue dye experiment. And then using a profile across that plume, we can see here, looking at the plume across after it reached its kind of terminal width. We've got elevated levels of air saturation, about 140%, 150%, and then a dramatic decrease down to maybe 60 to 80% outside of the zone where the oxygen is being input. And in this case, we got a plume width of about 3.3 or an alpha of about 1.6, which is narrower than what we got with the sodium hydroxide and blue dye, where it was more like 1.7, 1.8. We repeated this experiment again. In this case, the oxygen optrode was on the right-hand side. Again, you see the yellow and white zone where we have the elevated oxygen levels, over 100% saturation, similar to the plumes we saw before, but again, the width of that plume based on the profile where we've got the elevated oxygen was more on the order of 3 inches or an alpha of about 1.5. So at least in these two replicate experiments, we saw a narrower plume width with the oxygen plume compared to the plume width that we saw with the sodium hydroxide and the blue dye. Maybe this is due to the slower reaction rate that as we hypothesized. We probably need to run another experiment where we do the blue dye experiment with the inserted mesh screen and Permeox material in the center and see if that's impacting the permeability of the well sufficiently to cause the plume to decrease in size. If that setup gives us a similar result for the blue dye without the insert, then I'd say this is consistent with our hypothesis that the slower reacting material is resulting in a little bit narrower plume. But we need to look at that a little more carefully. We also looked at the pH. Remember, this is releasing hydroxide ions. And so we expect to see some elevated pH, but it turned out with our buffering solution, that really buffered that. It's a little hard to see here, but you can see near the center line of the plume, there's a little bit of an elevated pH plume, but it really was buffered out by our background buffer solution. So the next step was to look at a situation where we have a filter pack around our well screen. And in this case, as you see in this plot here of alpha versus K2 over K1, depending on the ratio of our permeability of the aquifer to the filter pack, we can get an alpha up to 4 times. So in that case, a 2-inch well screen would produce not a 4-inch plume, but an 8-inch plume. So this could be a dramatic effect. But you can see you really have to select the right conditions to be able to achieve that. So we set up our experiments with a filter pack. We had the 2-inch diameter, 0.06-inch slotted PVC screen. We put our media, our aquifer media was a 2030 mesh Ottawa sand. And then consistent with kind of the minimum borehole we would want to have with a 2-inch diameter well, we made a simulated borehole of 6 inches that was filled with the 2mm glass beads to be the filter pack. And then we put in the blue dye, similar before, and monitored the plume width downstream. Again, at an average pore water velocity of about 10 meters per day. So for these conditions, we ended up with a K2 over K1, the ratio of the well screen to the filter pack to the well screen permeability of about 2.1. So that would be down here. And if we come up, and this line here is plotted for the K3, so the ratio of the aquifer permeability to the filter pack permeability, a ratio of 0.36, the maximum alpha that we expect is about 2.5. So we can't get to that 4 alpha here. So we ran these experiments, and here we see the blue dye experiments, and you see consistent with the borehole dilution theory, actually we got a plume width that its maximum was about 4.75 inches. So that's an alpha of about 2.4, which is very close to what we theoretically predicted for our conditions. So then we did this with a reactive material. Again, the same setup, 0.06-inch slotted screen, 2-inch ID diameter, porous media, 2030 Ottawa sand, that's 6-inch filter pack of 2mm glass beads, phosphate buffer solution, in this case, pH 7 for the aqueous phase, 10 meters per day, approximate pore water velocity. In this case, these experiments ran sufficiently long, we had to periodically replace the sodium hydroxide so we can maintain a plume, and then we monitored the elevated pH plume emanating from the sodium hydroxide source using the pH optrodes. Again, we had half oxygen optrodes and half pH optrodes, so you're going to see half a plume. So you can see here on the left, initially the plume is developing similar to the blue dye experiments under the same conditions. We see some fingering of the plume coming out and elevated pH, up around 9 or so. And then if we watch it to the end of the experiment, we see a couple of things. Interestingly, I put a dashed line there roughly where that filter pack is, and you can see how initially it develops a certain width of a plume, and then when it hits the aquifer material, it extends out further, all right, consistent with our theory, and we get a little bit wider plume. So how does this compare to what we got with the blue dye experiments? Well, in the zone where we had the filter pack, we estimated the max plume width to be about 4 inches. That's an alpha of 2. It's a little bigger than what we got with the natural filter pack alone, which was about 1.8. I think that might be a little bit of an artifact of where we took that measurement. We took that measurement kind of in here where there's a little bit of a bump out of the plume there, and we may need to double check that. But anyway, it's similar to what we got for the 2mm glass beads alone. And then when we go downstream and we look at the plume and profile where we're into the sand aquifer, we're getting a plume width of about 5 inches or an alpha of 2.5, which is very consistent with our theory and our blue dye experiments. So based on these results, we believe that the borehole dilution theory gives good predictions of the plume width emanating from the well with and without a filter pack, very consistent with our experimental results. And so based on that analysis, then, if you want, under conditions where you just have the natural aquifer material around the well, and you want to get an alpha of 2, then the permeability of your well screen and its contents need to be at least 1 equal to the permeability of the formation. And if you want to get a little above 2, you need to be 10 times greater than the permeability of the formation. So you need to be very careful about selecting your well screen then, or just put, if you have cohesive material that you can put a borehole down and then backfill it with a reactive material, you can eliminate that. And then it's just important is the permeability of the material that you put inside the well screen. If you have a filter pack, you can theoretically get an alpha of 4, but the permeability of the well screen and its contents have to be more than 10 times the permeability of the filter pack, and the filter pack permeability has to be more than 100 times formation permeability. So you have to be very careful in selecting your well screens and filter packs to maximize the spreading of the reactive amendments so you can minimize the number of unpumped wells that you need to have across your plume. Typical monitoring well screens at 0.01 and 0.02 inch slots are probably not going to work very well. So when you're using, reusing existing monitoring wells, you really have to be careful. And with that, I'll stop. Sorry to run a little long there, but I'd be happy to try to field any questions. I just want to thank again Alex for all her assistance in doing these experiments. Abby Rates helped out early on from GMES department with getting this started. Jennifer Becker and John Gerke provide some early input on this project. Rob Fritz built our reactor. Department of Civil Environmental Engineering supported Alex with an undergraduate research grant, and then Presence supplied the equipment for the monitoring of the plumes. All right, thank you.
Great, thank you. So are there questions for Eric Seagren? That was really interesting. I'm gonna go ahead and I guess this is maybe more of a comment than a question, but it almost seems counterintuitive if I'm interpreting everything correctly, that to really get that maximum, plume width, you really need that big difference between the permeability of your well and your screen relative to the aquifer permeability. So am I correct in understanding then that it's hard to get a good plume development if your aquifer is very permeable?
If your aquifer is very permeable, yeah. So then you'd have a hard time getting good spread of your, if that's permeability is high relative to your material that you put into the well, the reactive material or the well screen. Yeah, that's true.
So, but in general, you would think that if you have a very permeable aquifer, then in general you would, well, perhaps not. You wouldn't get good mixing, good dispersion. So I guess it's a bit of a trade-off, and I don't know how common that scenario is. If you had just an extremely permeable aquifer, it might be hard to select a well screen that was more permeable.
Well, first, I think one way to think about that is, if the permeability of your well screen or the contents of your borehole is not very high compared to the aquifer material, there's just not much reason for that water to want to flow through there. Okay, and so the plume being captured through the well is going to be small, and then the plume coming out of it's going to be small. So that's why that. Does that make sense?
It does.
If you have a really permeable aquifer, you would just really have to have it would be you'd have to have a really high permeability inside you probably would then not even want to go with a well screen, just if you could bore a hole and put your reactive material into it with a very high permeability to draw that flow in and out.
Okay, thanks. It looks like that makes sense. It looks like Judith Perlinger has her hand raised.
Okay.
So go ahead, Judith.
Okay, and my question is along maybe the same lines of Jennifer's, Dr. Becker's. What about the influence of groundwater flow rate, or isn't it an issue with because groundwater flow rates just aren't that variable?
Well, I think that what, let's see if I, if you just look here, because the flow rate's proportional to the permeability or the hydraulic conductivity, it kind of washes out these expressions. And so the flow through these different zones is all going to be proportional to their permeability. And so it turns out, I think theoretically, we would have gotten the same results if we'd done them at a pore water velocity of 1 meter per day or 100 meters per day or 10 meters per day, because the relative effects of these different materials and their permeability is going to be the same. So the experiment would go faster or slower, but ultimately we would get to the same final point.
Okay, I think I follow. Thank you.
I don't know, that wasn't very satisfactory, I guess. But yeah, that ends up not being a factor here. What really is important is the size of these zones and the relative, their relative ability to transmit the fluids. John.
Well, thanks. I found that really interesting too. You and I've had discussions about some of this, and this one issue is something I can't remember what the conclusion was. So I'm going to bring it up again. Okay. And that has to do with the type of well screen. I think for the experiment with the filter pack, using the slotted screens that are cut into the PVC is not as conducive to spreading as if you'd used a wire wrap screen, like even a plastic one. And so I was curious if you had any and you were gonna try that, at least with the blue dye. And then I have a second question too, but I'd be happy to wait on that until let someone else ask a question.
Yeah, that'd be, like I said, we did this so that we'd had everything was the same except for the slot size. So it was kind of convenient to do that with these slotted PVC, monitoring well segments that we cut. But it would be interesting, to do it with different well screens, the same diameter, but different relative permeabilities. And we could, we'd see quite different results if they're more permeable, like a wrapped one, for example, like you mentioned. Yeah, I think it could have a big effect.
Yeah, well, a wire wrap screen will be, orders of magnitude higher,
right,
than the slotted.
Yeah. The other reason we got down is because I was thinking about also that, one way that it might be done is to repurpose a monitoring well. So this would be kind of not an atypical monitoring well construction. So what's going to happen if I put a reactive material down a monitoring well that I'm repurposing? So that was another driver here. But it would be interesting to look at some really high permeability screens, and we should then be able to get those kind of maximum plume widths. Yeah. But you got a second question.
Okay. Well, I was going to let, in case someone else does, but since you brought it up, I will. First of all, I'm going to shout out one of my undergraduate graduates, Leah Meek, is online. So this is a big draw that you did, Eric, because she's working as an engineer down in Sterling Heights, geological engineer, coming into this. That's awesome.
Well, I hope there wasn't a big disappointment.
No, it was worth it to me to be on here just to be able to chat with her a little bit.
Well, I'm glad there was at least one good aspect.
There was one redeeming aspect.
I can always count on you to make me.
Yes, sorry, you perpetuated that. But
yeah, I know.
Anyways, so this reaction rate thing, like with the blue dye isn't really a reaction rate, right? It's just diffusion and some hydrodynamic dispersion. And likewise with the oxygen, because you don't have anything in there consuming the oxygen, if I recall correctly.
No. Go ahead.
Related to that oxygen one, that background, was that like, the background was like 50, 60% oxygen, dissolved oxygen in the water. So the driving force isn't as great for the transverse dispersion when you have a background, that's roughly half of the concentration of what's in your dilution well, as compared to like the pH reaction, the acid-base reaction, where it's almost all consumed. The driving force is greater for that transverse dispersion.
Yeah, that's an interesting point. We deaerated this material, this solution, but then it's open to the atmosphere, and as is the tank. So we're getting oxygen constantly in from the atmosphere. So it was hard to keep it, really low. But I guess that would depend on if mechanical, and in this kind of scale, we can probably model this theoretically as combination mechanical and dispersion and molecular diffusion. So it would depend, if molecular diffusion was really important at this velocity, then that concentration effect, I imagine, could be more important. If the mechanical dispersion was more important, then the dispersivity, which would be the same in all of these cases, would be the important parameter, right? And I'm guessing that at this velocity of 10 meters per day, we're probably, and I didn't do this calculation yet, but it'd be a good thing to look at, we're probably in a range where mechanical dispersion is dominant over diffusion.
Well, certainly that's true in the longitudinal, but I'm just thinking in the transverse, because you're using a homogeneous, pretty well-rounded materials, that the transverse isn't, the hydrodynamic mixing may not be as much as
Yeah, that's a good point.
is telling you.
Yeah, that'd be a good point. Our experiments, space was not enough to really start to see that effect very much, right? Once our plumes formed, they stayed pretty consistent. We'd have to go quite a ways down gradient to see much of that dispersion effect. So, that could be a valid point that concentration could be having an effect there. That'd be something to look at. Yeah, it's a good point. Thanks.
Are there any last questions for Dr. Seagren? Okay, well, thank you again, everybody, for joining us today, and I'll be sending out information on next week's seminar very soon. So stay tuned. We have 4 seminars left, and in some of those seminars, we will definitely be hearing from some of our current graduate students, in addition to this work that Alex Waypa contributed to. So thank you again, Eric Seagren and Alex Waypa, and we'll see you again next week.